Hello, I'm Jeff Kolzak, Product Marketing and Applications Manager in the 8-Bit Microcontrollers Division. In this video, I will be taking you through the Programmable Switch Mode Controller, or PSMC Designer tool. The PSMC is a sophisticated peripheral intended to operate with little or no software intervention and provides up to 6 16-bit PWM outputs intended for power supply and motor control applications. The PSMC Designer tool is a graphical user interface, or GUI, that can be used to develop application software with the PSMC module. The PSMC module is found on the PIC16F178X family of microcontrollers. The number of PSMC modules present on the device range from 2 to 4 depending on which specific 16F178X device is chosen for the application. The PSMC Designer tool is a very handy tool that allows you a more visual way of using the PSMC module to set up your application. This tool can be downloaded from Microchip's website at microchip.com/PSMC and is very easy to install and execute. Once the tool is installed, a simple double click on the desktop icon will launch the tool. Once the tool is open, you will get a device menu allowing you to choose which device from the product family you want to use for the application. The drop-down menu here shows the various devices from the PIC16F178X family, as mentioned earlier. Here I selected the device, which is the PIC16F1782 and 1783. This device has 2 PSMC modules. Let's choose PSMC1 from the menu. On the tool, you will see the various blocks that can be individually configured in order to set up the PSMC module. These blocks include clock selection, timer selection, event generation methods like period event, rising edge event, falling edge event, blanking control, mode control, output control, and so on. We will now take a look at some of these important blocks in more detail. Here you will notice a checkbox in the GUI named PSMC Enable. This checkbox is used to enable or disable the currently selected PSMC. Similarly, there is an Interrupt Enable checkbox which enables or disables the corresponding bit of the PIE-X register for the currently selected PSMC. There are 2 other options: Timed Interrupt Enable and Auto Shutdown Interrupt Enable. Let's go ahead and check Timed Interrupt Enable. Coming to the control clock, you can choose either the FOSC or the 64 MHz source as the internal clock source. If an external clock source is needed, then go ahead and select PSMC-X clock pin from the drop-down menu. There are various prescale options to divide the clock from 1 through 8 to suit your clock requirements. This will decide the base clock in which the PSMC module will run. The timer control block can be viewed by clicking on the timer block in the main GUI as I am showing now. This timer is a 16-bit counter to which the synchronous period event, rising event, and falling event count registers are compared to create their synchronous events. Let's now click on the blanking block in order to set up the blanking control configurations. Blanking basically suppresses the selected inputs for a programmable period of time which starts at a rising event or a falling event, or both. All synchronous inputs pass through blanking. The 2 events that signal the output drivers to turn on and off are triggered using the rising and falling events. When a power driver switches from on to off state, or vice versa, it can cause spurious transients in the system that can cause false event triggers if not adequately suppressed. Modulation sources, however, the only input sources that are not affected by blanking. The blanking time can be entered in the appropriate text box in microseconds, and this is based on the count value calculated from the time base of the PSMC clock chosen earlier. Let's now open the period event block by clicking here. This determines the PSMC PWM frequency, and with each period event, the timer is reset. This period event source can be synchronous or asynchronous. Synchronous period event selection is made by clicking on the X leading to the upper input to the output OR gate. When clicked, the X is replaced by a straight line leading from the period time selection box to the output OR gate, as shown here. Synchronous period events can be deselected by clicking on the input line to the OR gate to change it back to a line terminated with an X. The synchronous period event frequency is determined by the time or frequency entered in the period time period frequency text box. The radio button below the box selects time or frequency as the display. When a value is entered, the period count value is calculated based on the PSMC clock frequency. Let's enter 10 kHz with the radio button selected for frequency mode. Asynchronous period events are selected by clicking on any X leading to the 7-wide OR gate of the control. Inputs are identified by a source signal name appended by a _B, which indicates that the signal first passed through the blanking function. Input selections vary by device. When all selections are open, the connection to the output OR gate is shown as open. The connection cannot be changed by clicking. Instead, it closes automatically when any asynchronous input is selected. Let's now move on to the modulation control block by clicking on it. Modulation is used in applications that need to gate the PWM output on and off. For example, infrared communications typically have a carrier PWM frequency to pulse the infrared emitters. This carrier frequency is then modulated on and off by the intelligence data. Let's enable modulation by clicking the Enable switch to the on position. When enabled, the modulation signal gates the Q output from the PWM SR latch to the PWM mode input. Note that the PWM coming into the modulation function is labeled Q, and going out it is labeled MQ. Modes that use the PWM signal take their input from the modulation function MQ output. When the modulation enable switch is in the off position, the MQ gate is always enabled, thereby passing the unmodulated Q output to the mode inputs. The mode control block is the heart of the PSMC PWM module. This forms the basis on which type of 16-bit PWM is decided and derived from the PSMC peripheral. Peripheral capabilities range from simple single-channel PWM generation to multi-channel complementary waveforms with deadbands between transitions. Let's look at a few of the important modes of the PWM and the intended applications which can benefit from these modes. There are 5 fundamental modes of operation, 1 high-resolution frequency mode, and 1 6-step mode that simplifies steering pairs of outputs to the 6 PWM channels. All modes except the 6-step mode have a corresponding complementary output mode, making a total of 13 modes achievable for the PSMC module. The complementary modes include 2 deadband controls, 1 triggered by the rising edge of the PWM signal and 1 triggered by the falling edge. You can select the different modes by clicking on the corresponding tab in the mode selection GUI as I am showing here. You have 6 different modes available here, like single PWM mode, single PWM complementary mode, push-pull mode, push-pull complementary mode, full bridge push-pull mode, full bridge push-pull complementary mode, pulse skipping mode, pulse skipping complementary mode, ECCP full bridge reverse mode, ECCP full bridge forward mode, fixed duty cycle mode, fixed duty cycle complementary mode, and the 3-phase PWM mode. There are up to 6 16-bit PWM output channels, and not all modes use all 6 channels. Unused channels are indicated by an output line that begins with an X. Let's look at a couple of modes and see how they can be configured and used. Here I click the Pulse Skipping Complementary or PSC Mode tab. Pulse skipping uses the asynchronous rising event output to enable the PWM output on a channel A. When the asynchronous input is low at the period event, the PWM output on channel A for that period is suppressed. Otherwise, the PWM output would be generated normally as it would in the single PWM mode. The complement of the PWM output on channel A is generated on channel B. The deadband from this mode can be configured by clicking on the deadband block and entering the time in microseconds. The pulse skipping mode is generally used in hysteretic power conversion applications. Let's now look at another mode. Let's click on the ECC PF or the ECC PWM full bridge mode in forward direction. The ECC compatible PWM mode is forward direction is a full bridge driver with 2 or 4 channels, channels B and C active. The channel B output is a PWM drive and the channel C output is true without pulse width modulation. This mode is intended to drive the high side and low side of opposite sides of an H-bridge power device configuration. These are mainly used in brushed DC applications that need both speed and direction control. The mode is compatible with the full bridge mode of the ECCP peripheral. This mode can be changed to the reverse direction mode by clicking on the direction switch or clicking on the ECCP R tab. When the motor is running and the direction is changed, the change is synchronized with the period event and the deadband time is inserted to prevent shoot-through on either side of the H-bridge. Moving on to another important mode called the three-phase PWM mode. Here I've clicked on the 3PH tab. The three-phase PWM mode is used to generate waveforms for 6-step three-phase systems. The brushless DC motor drives are one example where this PWM mode is very useful. These systems have 3 half-bridges requiring 2 drive outputs each for a total of 6 channels. This mode uses the steering control bits to drive 2 of the 6 channels at a time, namely one half-bridge high-side drive and another half-bridge low-side drive, both kept on at the same time. The various channels are directed to the output pins through the output control. Here I've opened the output control GUI by clicking on the output control block. There are 4 selections for each channel in this control: output enable, output steering, output polarity, and shutdown level. The output enable switch selects between the port latch output and the PSMC channel. When the port latch output is selected, the output pin is not affected by the PSMC. When the PSMC channel is selected, the pin is not affected by the port latch. There are 2 options for transferring the completed PSMC configuration to your project. One is to copy the code into the clipboard buffer, which can be pasted into your source code. The other transfer method is to generate an output file that can be included by reference in your source code. Include files are also the means by which PSMC configurations are stored for later retrieval by the PSMC designer. The file menu allows you to generate and save the assembly code or C code, or you can even load a previously saved PSMC configuration setup. One other option of the tool is that you can comment whatever information you want relevant to the project, and this would appear as a comment in your assembly code or C code that the tool generates. Having about 30 registers in the PSMC module, it can be an overwhelming task to configure each of the registers in order to get the desired output from the PSMC module. Hence, the PSMC Designer tool was created, thereby simplifying this effort as was shown in this video. You can find more information on this tool at microchip.com/PSMC.